OCR A-level physics. This is the third video for circular motion and SHM, and this video is about energy and SHM. So look at this mass on a spring oscillating. What kinds of energy are involved? Well, when the spring is compressed or when the spring is stretched, then we're talking elastic potential energy, which is, remember, that's a half kx squared. When the spring is when the spring is relaxed, when the mass is in the middle, then we're talking kinetic energy. So basically what's happening is that the energy is potential energy, kinetic energy, potential energy, kinetic energy, potential energy, etc. And it's continually being sloshed between potential energy and kinetic energy. If it's undamped, and I'll talk a bit more about that later, then the total energy stays the same. Similar for a pendulum. For a pendulum, the bob actually moves vertically. So we get gravitational potential energy to kinetic to gravitational potential energy, etc. So in SHM, energy is repeatedly transferred between kinetic energy and some form of potential energy. And looking at this graph of energy against time, you'll see there's the potential energy and the kinetic energy, and the total is constant if it's undamped. As well as that graph, you need to know this graph. Again, for an undamped free oscillation, this is how the two types of energy vary with displacement. So displacement, we've got x equals 0 in the middle, and then you've got your maximum displacement is A, and you'll see that the potential energy is a maximum there, the kinetic energy is 0, the same on the other side. In the middle at x equals 0, the potential energy is a minimum and the kinetic energy is a maximum, and again the total energy is constant. Two types of oscillation we're going to talk about. So you've got free and forced. A free oscillation, if I get a pendulum and I just pull it to the side a little bit and let go, then it oscillates freely at its natural frequency. So you give an object an initial displacement, like you pull a pendulum to the side or you lift up a mass and let go, and it will oscillate at its natural frequency, and that is a free oscillation. A forced oscillation is if you actually make something oscillate. If there's an external driving frequency, like there's Peter with his maracas and he's picked them up and he's shaking them at a certain frequency, yeah, and that's the driving frequency. For example, your car engine gives off lots and lots of vibrations, and anything attached to it will vibrate at that frequency. Okay, that's a forced oscillation. I'm also going to mention damping now. Now, damping is the oscillator, every cycle, it will lose a little bit of energy due to friction. Okay, for example, the pendulum will lose a little bit of energy every cycle due to air resistance, and this is called damping. So a free oscillation doesn't last forever in real life. The amplitude will get smaller and smaller because every cycle you lose a little bit of energy due to some kind of friction. You can actually increase the amount of damping to, if you don't want these oscillations happening. For example, on a vehicle, like this is a shock absorber off a motorbike. And basically there's lots and lots of damping so that you don't want your bike bouncing up and down for ages after you've run over a speed bump or something. Okay, so shock absorbers are actually designed to increase the amount of damping. This is an experiment you should definitely be familiar with. We have a signal generator, we have a vibration generator, and we have a mass on a spring. And what we're doing is we are measuring the amplitude of the mass. So the amplitude of the mass on this fantastic animation is about there. So there's your amplitude there. Now, you start the experiment with the mass not moving, and then you, in increments, bit by bit, you increase the frequency of the vibration generator and you measure the amplitude of the mass. Then you plot a graph of the amplitude of the mass against frequency and you get this. Now, looking at this graph here, you should clearly see that at a particular frequency, we get very large amplitude oscillations. Okay, at very, very low frequency, then the amplitude of the mass is just the same as the driving amplitude. Yes, they go up and down together, but then the amplitude of the mass gets bigger and bigger and bigger, and we get this peak, which is called a resonance peak. And then at higher frequencies, it goes down again. At very, very, very high frequencies, then the amplitude of the mass is almost zero. Okay, but the important thing here is that the amplitude is greatest when the driving frequency is equal to the natural frequency of the system. And this effect is called resonance. Remember, learn this sentence. When the driving frequency equals the natural frequency of the system, we get large amplitude oscillations. This is called resonance. Why it happens, you can think of it as pushing a kid on the swing. If you give the kid a push at just the right time, then the amplitude of their swinging will get bigger and bigger and bigger. If you give them a push at any other time in the cycle, then it won't. Yeah, at a different frequency, then it won't get bigger and bigger. It may come up, if we increase the amount of damping, how will this graph change? Well, with more damping, then the graph will look something like that. We say that the resonance peak won't be as sharp. Okay, if you go on and do engineering, you'll learn about something called the quality factor of the resonance peak. Lots of examples of resonance. Resonance can be useful, but it can also be a problem. Go on YouTube and see if you can find a video of somebody smashing a wine glass by singing at it. If you sing a particular note very, very loud, you can actually get a wine glass to shatter. Yes, if that note is equal to the natural frequency of the glass, then you get large oscillations, large amplitude oscillations, and the glass shatters. Hopefully you've seen the Tacoma Narrows Bridge. This bridge in America, which cost millions to make, and then it only lasted a couple of months because the wind blowing down the valley made it oscillate and it fell to bits. Water molecules can absorb microwaves at a certain frequency, and that makes the food hot. Has to be just the right frequency to get them to resonate. Buildings like skyscrapers, they can resonate if caused by maybe an earthquake or caused by the wind. So when you're designing a skyscraper, you need to think about maybe putting some damping in there to reduce the amplitude of these oscillations. Musical instruments, whether it's a string instrument like a violin or a guitar, the sound box, yes, this box that is designed to resonate and make the air inside resonate, and that makes the sound much louder. Wind instruments, the air column inside resonates, and it resonates at different frequencies when you introduce nodes and antinodes by putting your fingers at certain places. When we do medical physics, we'll talk about MRI, which is magnetic resonance imaging. You can actually get protons to resonate, yeah, by changing the way that they spin. The car engine is going to produce a huge amount of vibrations, and unless it's very, very well damped, then lots of other bits of your car will resonate, which you don't really want to happen, probably. Lastly, Demonstrating resonance in a lab, hopefully you've seen Barton's pendulum. You have a heavy pendulum like this 300-gram mass here, and it's attached with a bit of string to lots of other very, very light pendulums, yes, pendula, of different lengths. And when you get your driver pendulum swinging, one of the other ones is going to go crazy. Yeah, one of the other ones will resonate, and see if you can figure out which one and why. And I'm not going to tell you.